Good morning, sir, classmates, and listeners. In today's discussion, we're delving into material selection and consideration, a cornerstone in tech innovation. In the next 15 minutes, we will cover first, historical background, which is understanding how material choices evolve with technology. Second is description and definition, exploring types of materials from metals to polymers. Third, structures, learning about crystalline and amorphous structures that affect performance. Fourth, processing, unveiling techniques like casting or extrusion that shape materials. Next is properties, discovering how materials differ in mechanical, thermal, and electrical aspect. Next is the advantages and the disadvantages, weighing the pros and cons of material use. Next is applications, seeing how materials play crucial roles in aerospace, construction, and electronics. And lastly, the future trends, peeking into upcoming trends like nanomaterials and sustainable options. Remember, material selection is not just technical. It's an shaping, or it is an art shaping our engineered reality. Material properties. Material properties refer to the characteristics that define the behavior and performance of a material. These properties include mechanical, thermal, electrical, and optical properties. In material properties, it can be classified into physical, mechanical, and chemical properties. Also in physical properties include density, melting point, and thermal conductivity, while mechanical properties include strength, stiffness, and toughness. The material properties chosen for a product have a direct impact on its performance, reliability, and lifespan. For example, selecting a material with a high strength is crucial for applications where load-bearing capacity is essential. Examples of material properties and their effects including using a lightweight material like aluminum in the aerospace industry to reduce fuel consumption, and selecting a material with high electrical conductivity for efficient electronic devices.
The evolution of material selections reflects a journey shaped by scientific and technological progress. Imagine, it is a series of significant steps. First, the discovery of metals, then the advent of polymers, and advancement in ceramic and composites. Influential figures like Marie Curie and Charles Goodyear played pivotal roles in these milestones, leaving a lasting impact on the field's growth. These historical developments continue to echo in our modern practices, influencing how we choose materials today. The alloys in our structures, the polymers in our everyday items, and the materials in cutting edge of technologies all bears the traces of this journey. This blend of past wisdom and ongoing innovation for the basis of dynamic approach to material selection, inspiring inventive solutions for contemporary challenges.
Material selection is a critical process in engineering and design, involving the careful choice of materials based on their specific properties and performance characteristics. This strategic decision-making ensures that the selected materials align with the intended purpose of the final product, considering factors like mechanical strength, thermal conductivity, cost-effectiveness, and environmental impact. Materials can be broadly categorized into metals, polymers, ceramics, and composites, each possessing unique attributes that influence their applications. Metals known for strength, fine use in the structural components and electrical systems. Polymers, including plastics, offers versatility and are commonly used in everyday items. Ceramics prized for durability and thermal resistance are employed in high-temperature applications and electronics. Composites formed by combining different materials provide tailored properties to meet specific demands. Further classification, based on properties such as conductors, insulators, and semiconductors, allows for precise material selection. Common examples within these categories include steel, plastic, glass and carbon fiber, showcasing the diverse energy of materials available for truthful consideration in the design, and engineering process.
Materials derive their unique properties and behaviors from the interfaces of their atomic and molecular structures. At the atomic level, the arrangement of elements forms the foundational for microscopic traits, dictating how materials respond to external forces and conditions. The microscopic architecture serves as the language of materials, unveiling insight into their mechanical strength, thermal conductivity, and electrical properties. Crystal structures with their cubic, hexagonal, or otherwise represent a Purgosian aspect of materials science. This higher level arrangement profoundly influence microscopic behaviors. For instance, the crystalline structures of metals contributes to their malleability and conductivity, while ceramics often exhibits high hardness and resistance to do heat to specific crystals. Arrangement, this link between atomic structures and crystal formation serves as a fundamental blueprint crystals for understanding and harnessing materials for diverse applications. Additionally, delving into the microstructure, which encompasses the arrangement of grains and pieces within materials, provides crucial insights into overall performance and durability, highlighting the interconnectedness of atomic structures and material behavior on a larger scale.
Identifying design requirements, understand the functional, aesthetic, and performance needs of the product, helps establish the criteria for material selection. For instance, a smartphone requires a material that is durable, lightweight, and visually appealing. Evaluating materials option through research and comparison of different materials based on the properties, availability, cost, and environmental impact is essential. Materials can be sourced from databases, supplier catalogs, or drawn from previous experiences. Material testing and analysis, conducting tests and analysis to validate the properties and performance of the materials under a specific condition is crucial. This may involve mechanical tests, thermal analysis, and compatibility assessments. Final selection criteria. Based on the evolution of testing, a final material choices is made considering the factors like performance, cost, availability, and manufacturability. The use of material selections matrix or decision-making tools can facilitate this process.
Material properties refers to the characteristic of defined behavior and performance of a material. These properties include chemical, thermal, electrical, and optical properties. Material properties can be classified into physical, chemical, and mechanical properties. Physical properties include density, melting point, and thermal conductivity, while mechanical properties include strength, stiffness, and toughness. The material properties chosen for a product have direct impact of its performance, reliability, and lifespan. For example, selecting a materials with high strength and crucial for applications where load-bearing capacity and essential example of material properties and their effect include using and lightweight materials like aluminum in our aerospace industry and reduce fuel composition and selecting a materials with a high electrical conductivity for efficient electronic device.
Advantages and disadvantages of material selection and consideration. There are many advantages of material selection and consideration, such as optimized performance. It is selecting materials with specific properties allows for optimization of product performance. For example, using lightweight alloys in aerospace applications enhances fuel efficiency and overall performance. Second, cost efficiency. Strategic material choices can lead to cost efficiency. For instance, opting for corrosion-resistant materials in marine engineering reduces maintenance cost and extends the lifespan of structures. Third, sustainability. Considering environmental factors in material selection, such as using recycled or eco-friendly materials, contributes to sustainability goals and aligns with increasing societal awareness of environmental impact. But there are disadvantages of material selection and consideration. First, complexity. It is the vast array of available materials and their complex properties can make the selection process challenging, potentially leading to errors in choosing the most suitable materials for a given application. Second, cost of testing. Testing materials for specific applications incurs cost, and the expense associated with thorough testing can be a drawback, particularly for smaller projects or those with budget constraints. Third, rapid technological changes. Advances in material science may render existing materials obsolete, requiring continuous adaptation to stay abreast of the latest innovations and select materials that align with cutting-edge technologies.
Material selection and consideration play a pivotal role in diverse industries. In aerospace engineering, the strategic choice of the lightweight alloys like titanium ensures optimal fuel efficiency without compromising structural integrity. Biomedical applications, particularly in medicinal plants, demand in biocompatible and corrosion-resistant materials. With titanium alloys, iron prepared for orthopedic purposes. Its construction material selection, such as reinforced concrete, is vital for ensuring structural durability and safety. The electronics manufacturing sector relies on materials with specific electrical properties, with semiconductors like silicon being fundamental to electronic device manufacturing. Similarly, in the automotive industry, the use of advanced composites including carbon fiber reinforced polymers contributes to weight reduction and improved fuel efficiency. In each application, material selection addresses specific requirements, influencing the overall performance, safety, and efficiency in the end of product.
Future trends in material selections and consideration. The trajectory of material selections is poised for transformative shift with 2K strength shipping. The future and landscape. First and foremost, there is the discernible move toward and the integrations of smart materials. This is materials exhibit responsiveness to external stimuli such as temperature change or mechanical stress. Introduction adaptive functionalities. This trend holds promise across diverse sectors regarding from her self-healing materials and constructions to the utilizations of shape, memory, alloys, and isopos. Applications, the incorporations, smart materials, heralds, an era where structures and device can be dynamically respond to varying conditions, enhancing realizations and efficiency in unprecedented ways.
There is a pronounced shift towards adopting circular economy principle in material selection. This entails a strategic focus on recyclability, reusability, and minimize environmental impact throughout a material's life cycle. Industries are increasingly embracing materials designed for easily disassembly and recycling, aligning with broader sustainability goals. This trend represents a fundamental commitment to environmentally conscientious manufacturing practice, making a paradigm shift in how materials are selected and utilized. As these trends converge, the future of material selections is characterized by a dynamic interplay for innovation, adaptability, and steadfast commitment to environmental responsibility.